All right, I want to do the photoelectric effect in like high speed. Okay. Now, solving why this photoelectric effect happened is why Einstein won his Nobel Prize. So this is how we're going to look at this. So the first thing you need to have is you need to have like a vacuum chamber. So let's draw a vacuum chamber. It's like a glass tube, essentially, right? A glass tube that we've sucked all the air out of. And then what we do is we, inside of here, we put some sort of metal plate, okay, on one side. And on the other side, we just put another metal plate, doesn't really matter what it is, okay? And then we hook this up to a voltage source, and then we put an ammeter on here. All right, so we just leave this be, leave it in a dark room. Nothing's gonna happen, okay? And let's say we fire this up to like 8 volts or 10 volts, doesn't really matter. Still, nothing's gonna happen. But then we take some light, okay? We put a light bulb here. Okay, there's a light bulb, and we shine the light bulb on here. What we will notice is that if we change the color of the light, say we go from red, and then we go to, say, green, and then we go all the way up to purple, okay? Well, what we're doing is we are changing the frequency of the light, right? We're increasing the frequency of the light. Eventually, somewhere along this spectrum, we will notice that a current starts to flow. So a current starts to register on our ammeter. So what does that mean? Well, what that must mean is that, and I have this backwards, I just realized. I don't want to get in trouble from eagle eyes. So let's just make sure we put this the right way. This has to be the positive side here. So we've got a positive electrode there, and we've got a negative one here. And let's just say this is made of like a certain type of metal. I don't care what type of metal. We call it aluminum. And in fact, we're going to change out what metal is on here. We're going to change it out as we do our experiment. So as we increase, right, our intensity, we move it this way, more towards the purple end, more towards a higher frequency light. Eventually, at some point, all of a sudden, current will start to flow. What that means is electrons are being freed from the metal and zipping across here and registering as a current in the system. Once we reach that very specific frequency, if we increase the intensity or brightness of the light, we will find that we suddenly get a higher current. If we, however, drop the frequency back down, no matter how bright this light is, right, no matter how intense it is, you'll get no electrons. So how do you explain this with a wave? And the answer is you can't, okay? Because waves are transfers of energy, and they are not quantized. In other words, you leave a wave going, and it's just going to keep building up energy as it goes, and eventually this is going to get warm enough to spit off electrons. Or, you know, however you want to look at it, the electrons that are in this metal are going to gain enough energy to spit off. And that is not what happens. You can leave this light on all day. If it's below the cutoff frequency, you get nothing. You get no current coming out. So how is this explained? Well, going into this, it was considered fact that light was a wave, or it was at least agreed upon that it was mostly like a wave. Things like Young's double slit experiment sort of showed that it must have a very wave-like nature. However, if it's really a wave, you wouldn't see the photoelectric effect like you do, right? You wouldn't have a cutoff frequency, because if you took like, you know, red light and you just cranked up the intensity, you'd be shooting more energy in these things, and it wouldn't make sense that eventually you wouldn't get some electrons spitting out of here. So how is the explanation of this? So here it is. You have various different metals, right? You might have sodium, you might have like aluminum, and so on. And if you think about the Bohr model, which is also like a quantum physics model of, you know, of these atoms, you know, with sodium, for instance, you have this kind of an arrangement with one electron in the outer shell, right? But you have these energy levels, and we know from chemistry class that there are other energy levels up here that are just unoccupied, and that, you know, if you excite these electrons, they can like move up to higher energy levels. Okay. All right. So in this case, let's say that we have sodium here, right? Eventually, you're going to get to a point where the frequency is high enough that this electron is going to leave the sodium, right? It's going to travel out of this atom. So how do you explain that? Well, Einstein said what's going on is these electrons are absorbing photons or particles of light. Particles of light. And if that particle of light has enough energy, that electron absorbs it and it zings right up out of the atom, and it can leave, right? It can get right to the surface, or it can travel away outside of these energy levels, and it can actually become part of this flowing current, okay? But if this particle comes there and it doesn't have enough energy, well, your electron might only get to here, and it's going to fall back down. It's going to stay trapped inside of this atom, right? So how do you find and how do you relate the photon, right? These particles are called photons. How do you relate the energy of a photon to what's going on here? Well, you use this little formula, E equals hf, where this is the frequency of light associated with, this experiment. This is Planck's constant, who was the first to discover that energy was quantized. Einstein didn't discover it. And this is the energy of the photon of light, okay? If the energy of the photon of light is high enough, in other words, if the frequency of the light is high enough, it might have enough energy to actually split this electron off, right? But if the frequency is too low, that electron won't make it off of there. So now we got to think about light in a different way. Instead of thinking of it as a bunch of waves, we now have to think of it as a whole bunch of little particles firing off of here. And how much energy each particle carries with it depends on the frequency. E equals hf equals hf. Okay, that's how much energy each one of these particles or photons has. And if it gets enough, then it can free an electron. The electrons can absorb it, and they can zing up to a higher energy level. And if it has enough energy, they'll actually leave and become part of the current. Okay, so the minimum amount of energy that you can have to get an electron to just the surface of the atom but not leave is called the work function, WO. It's the minimum amount of energy that you can have, okay? If you have more than the work function, then these electrons zing off of here with a little bit of energy. We call that EK, kinetic energy, right? They're moving. So our energy in our photons, the energy of the photons, we'll call it EP, has to have enough energy to equal the work function plus whatever extra energy beyond the work function gives us EK. Now you can find like big charts of work functions and figure out what sorts of photon sizes you're going to need to do that. But all the work function means is just what's the minimum amount of energy we can put in to this particular metal to get its electron to the surface. If we go at higher energy than that, right? We go at higher energy, then those electrons come screaming out with some velocity, and they can actually leave and become part of the current. Okay? So HF then just has to be equal to this. HF, the energy of the photon, has to be equal to the work function energy plus the kinetic energy, 1/2 mv squared. And this is a little bit beyond where we need to go. I'm just going to write the math just because. Now let's think about it. Once we get to photons equal to the work function, if we increase the intensity, all we're doing is adding more photons, right? You add more photons, you get more electrons, you get a higher current, right? If we leave it at the same intensity, but we increase the frequency, you don't get more electrons because you don't get any more photons. But what you do get is you get energy of these electrons coming out with a higher kick, right? They come zipping out faster if you want. That's not really going to register a change in current, okay? So that's the photoelectric effect, and that's why light has to be thought of as not only a wave but a particle as well. I did it. And the work